Yes, let's start. In the previous classes, we have seen about the code generation phase and the issues that were present in the code generation phase, various issues that were in the code generation phase. So, in following that, we are going to see this topic called as basic blocks and flow graphs. So, what this basic blocks is that we have seen about the intermediate code, correct? We have seen about intermediate code, and the intermediate code, when it is represented in the graph representation in the graph mode, that is called as the nodes that are present in the graph is called as the basic blocks. And so when you say a graph, definitely it will have nodes as well as the edges that connects those nodes. Okay, so here the edges would be the we will be creating some basic blocks, and that basic blocks will have the connection which says that after completing executing this instruction, the next is which one. Okay, that goes there. So usually this kind of basic blocks graph would be helpful in the register allocation as well as the instruction selection, because this is what we have seen as the main tasks of the code generation phase. So kindly wait.
Excuse me, ma'am. Ma'am, I guess you're on mute.
Okay, okay, sorry, ma'am. Okay, let me tell you again. So basic block is nothing but the maximal sequence of consecutive instructions. So we have already studied about the three address instructions. Okay, so three address code we have studied many three address instructions. So in the three address instruction, if you have if you have some list of 10 instructions, say, okay, so which are all the instructions that could be executed in a consequence, and what is the maximum sequence of instructions that you could execute in a single flow? Okay, so if you have a set of some five instructions in a basic block, then the control will start from the beginning of the block, and it will end at the last instruction in that block. Only then the control will flow outside. So now if you have some 10 instructions in the basic block, then for example, say you have some four blocks in the four basic blocks. So for example, you have two instructions in the first block, again three instructions in another block, again another three, and another two. Okay, so all these instructions that are present in the basic block, it would be unique. Okay, each instruction is assigned to exactly one basic block. Okay, so now we will see how we have to create the basic block. So we we have taken an example here which contains some 17 three address instructions. So now we need to convert this, or we have to partition this set of three address instructions into basic blocks. So how we can do that is, we need to find out which are all the instructions would come inside each basic block. So for that, first initially we need to find out the leader of the basic block. That is, we are going to determine one instruction as the leader of one basic block. Okay, if this particular thing has, so if it is going to be partitioned into some three basic blocks, assume, then each basic block, the first instruction would be the leader of that particular block. So first we need to find out which are all the leader instructions. Okay, from this set of 17 instructions, we need to identify which are all going to be the leader instructions. So to determine the leader instructions, we have certain conditions. How we can identify the leader instructions? We have three ways in which we can identify the leader instructions. The first one is the first three address instruction, the very first. The very first three address instruction would be the would be a leader instruction. Okay, so here in this case, we have the first instruction, say I is equal to 1. So this I is equal to 1, this is a leader instruction. Okay, and the second condition is that any instruction that is the target, you need to notice this word, target of the conditional or unconditional jump is a leader. Okay, any instruction that is the target of a conditional or unconditional jump is a leader. So which is a jump instruction here? We can see here in the ninth instruction we have something called go to of 3. So what it means, if j is less than or equal to go to 3, so it is a jump instruction. And similarly here also we have a statement say go to the instruction 2. So that means this is also a jump instruction, and here also we have a jump instruction. So now what this thing says, target of the conditional or unconditional jump. So for this jump instruction, which is the target, the third instruction is the target. Okay, so this instruction tells it to go to the instruction tree. This is the target, and for this one the target is the second instruction. Okay, so that means this is a leader, this is a leader. Okay, and similarly here it says that go to 13. So this 13th instruction, this is also a leader. Okay, so now we have identified four leaders up to now. So according to the first case, the first three address instruction, it is a leader. And according to the second case, the target of a conditional or unconditional jump. So we have three jump statements here, and these instructions whose target is the second instruction, the third instruction, and the 13th instruction. So all these are also leader. So now the third case is any instruction that immediately follows a conditional or unconditional jump is a leader. So now we have seen the conditional jumps or the unconditional jump statements here. So whichever instruction that immediately follows the conditional or the unconditional jump is a leader instruction. Okay, so that means we have so we have now after the jump instruction, what are the instructions we have? We have the instruction. We'll see the example. So the instruction that immediately follows the conditional or unconditional jump, that is, so we have the jump instruction here. Okay, this is a jump instruction, this is a jump instruction, and this is also a jump instruction. So what immediately follows that, that is again a leader instruction. Okay, whatever that follows that would be a leader instruction. So here after this jump instruction we don't have any other jump instruction, we don't have any other instructions. Okay, so after the jump instruction, whichever instruction is following, that is a leader instruction. So now the basic block will start with the leader instruction and stops before the following leader instruction. So now what are all the leader instructions we have found now? The first instruction is a leader instruction. So second instruction is a leader instruction. Okay, because we have a that second instruction is a target of this jump instruction, and also third is a leader instruction because that is the target of this jump instruction. And then we have the instruction that the immediately follows the jump instruction. Okay, and we have this 13 is also a leader instruction because that is the target of this one. And whichever that follows the jump instruction, that means this following this jump instruction is the instruction number 10. Okay, so 10 is a leader instruction. And then we have, after this jump instruction, we have instruction number 12. So that is also a leader instruction. Then here we have a jump instruction, but after that we don't have any other instruction to follow. Okay, so now what are all the leader instructions? 1, 2, 3, 10, 12, and 13. And what is the basic block? basic block starts with the leader instruction. Okay, so the first basic block starts with the instruction 1, leader instruction, and stops before the following leader instruction. The next leader instruction is again 2, so that means that is a separate block. So now this block, it has only one instruction, and this block starts with instruction 2, but then again 3 is also a leader instruction. Then it means that 3 is a separate, the 3 comes in the separate block. So in the second block we have only one instruction, and then what follows that is 10. So from 3 to 9, okay, from 3 to 9 we'll be having the instructions in the same block. So let us say that this is block 1, this is block 2, and this is block 3, and the next instruction, next block leader is the instruction number 10, and it will have up to 11. Okay, because 12 is again another leader, so that is again another block. So this is block number say 4, this is block number 5, and then again we have we have another leader, which is instruction 13. So instruction 13 to 17 is next block. Okay, so we have 1 2 3 4 5 and 6 blocks will be having out of this 17 instructions. So now this is how we need to identify the block leaders for each of the basic block, and we need to construct the basic blocks. So once an intermediate code program is partitioned into basic blocks, we represent the flow of control between them by a flow graph. So now what we have done is we have identified the nodes. So now we need to connect them using the edges. So that is, we need to find out, or we need to represent the flow of we need to represent the flow of control between them by a flow graph. Okay, so the nodes of the flow graph are the basic blocks, and when there will be a edge, is that there is an edge from, say, from block B to block C. Okay, in block B assume that you have some 9 to instruction 12, and in block C you have the instructions from 13 to 17. So there is an edge from block B to block C if and only if it is possible for the first instruction in block C to immediately follow the last instruction in block B. Okay, so you have executed the instruction 12 in block B, and if you are going to continuously execute the next instruction from block C, then we will have a edge between these two blocks. So how we can justify these edges is that there is two ways in which we can do that. The first one is there is a conditional or unconditional jump from the end of B to the beginning of C. Okay, so already we have seen about the conditional or unconditional jump statements, and if there is a jump statement or the jump instructions from the end of B to the beginning of C. Okay, so from in the end of B, you have a jump instruction, and whose target is, if it is present in C, then we'll have an edge. And C immediately follows B in the original order of the three address instructions, and B does not end in an unconditional jump. So if the original order of instructions is followed there in the basic blocks, then also it will have a edge between them. So now you can see the basic, you can see the flow graph here. So now already we have seen which are all the leader instructions. Okay, we have identified we have identified 1 as the leader instruction because that is the very first 3 address instruction, and 2 is a 3 address instruction, and 3 is a 3 address instruction because these two and the instruction 3, these are the targets of some jump instructions. So that is also a leader instruction. And then we have seen after the jump instruction, the instruction that is immediately following that is also leader instruction. So we have seen all these things. Now see, now this becomes a separate basic block. We call it as B1. And then 2 is separately a block. Okay, so that is what shown here. And from 3 to 9. Okay, so from this instruction till this one. Okay, you can see 1, 2, 3, 4, 5, 6, 6 instructions. This is present in basic block B3, and B4 we have from 10 to the next one, 10 and 11 or the B4. These two instructions form another basic block, and this instruction separately forms a basic block, and then from 13 to 17 the next block. Okay, so we have totally 6 basic blocks. And see the edges now. Now there should be an edge from one block to another block only when, if you are going to execute, so after executing this instruction, if you are going to start executing the beginning of the next block, then you will have an edge between them. Okay, and you can see here, here in this basic block B3, you have the last instruction says go to B3. That means it is a self loop. Again, it goes back to the same beginning of the B3 block, and it will again do this. Okay, until this condition becomes false, this loop will execute. If it is false, then again it will go to B4. Similarly, here also in B4 we have a jump instruction which says if this condition is true, go to B2. So it goes to the basic block B2, and then if it is false, it comes to B5, then it comes to B6. Similarly, here also a jump instruction. If it is true, then again it will have a self loop. Okay, so once all, when this condition is false, then it comes out, and that is the exit of your program. Okay. Now in this, one important thing that we need to understand is that in this we have now constructed the basic blocks from the 3 address instructions. So now we know what is the leader instruction and how to construct each basic block using the leader instruction. Okay. Now we assume that the symbol table initially shows all the non-temporary variables in the block as being live on exit. So for example, you have the so inside each basic block you have a set of instructions, and there you use several variables. Okay, if you could look into the previous thing. Okay, for example, if you take this first particular block, you have a variable I, then you have a variable j here, and here you have several variables again, I, j, and also some temporary variables are also there, but we talk about only the non-temporary variables. So again, I and j are here. So similarly, you will be having the variables used in the various basic blocks. Now, we have already studied about the symbol table. So in your symbol table, initially when this basic block is constructed, it will have one field which will have the information about this variables, whether it is live or not. Okay, live means it will be used again by some other statement or some other instruction. So initially it is given as being live on exit. Okay, when you come out of the basic block B, okay, for example, you have a block B and you have some variables, say I, J, and so on. Now in the symbol table, for this variables I and j, you initially you make it as live. Okay, that means this will be used after that. But the output is that at each statement, say for example, you have a statement I where you have an instruction called x is equal to y plus z. Okay, now we attach to I the liveness and the next use information of x, y, and z. So this is statement number. Okay, so so for example, you have the instructions say 13, 14, 15, 16, and so on. Okay, in a single basic block. Now this is the statement I, we can say. Okay, statement numbers, and you have some instruction here. Okay, x is equal to y plus z, I is equal to I into 10, something you have. Okay, now for each of these variables we have in this thing, we are going to attach two information. Okay, one is liveness and the next use information. So in each of these statements, we are going to tell what is going to happen for this variables x, y, and z. The sometimes that information may not be used after that at all. Okay, so what we are going to do is we start at the last statement in B and scan backwards to the beginning of B. Okay, understand, if in a block you have some 1 2 3 4 and 5 instructions we are having. Okay, 5 3 address instructions we are having in one basic block. Now in this basic block we are going to start scanning backwards. That is, we start from the last instruction or the last statement in this basic block, and we are going to scan backwards towards the beginning. Now at each statement, in this for example, we take this statement x is equal to y plus z. Okay, this is one of the statement in the basic block. So for every statement, what we are going to do is attach to statement I the information currently found in the symbol table regarding the next use and liveness of x, y, z. So currently, in the symbol table, for all the variables that you are going to use in that basic block, there is some information that is given about the liveness and the next use, when this particular variable or this value is going to be used in the program. Okay, so initially we are going to attach whatever is present in the symbol table at present. Okay, and then in the symbol table set x to not live and no next use. That means we are assuming here this x is, so here we are going to have the statement is x is equal to y plus z. So y and z are added, and the result is going to be stored in x. Now, if this x value is not going to be used after this, okay, if this, for example, if the next statement says a is equal to x plus 1, okay, then it means that this x value you are going to use in another instruction. But we assume that this x is not going to be used anywhere else. Then what we can do is, the in the symbol table initially the x value information is given as live, and also next use would be there. But now we update it that it is set to not live and also no next use. Okay, we are going to we are going to update it in the symbol table. Okay, this for example we are taking because we assume that x is not going to be used anymore in the program. And we assume, let us assume that y and z are going to be used in the program later. So for example, a is equal to y plus 2 and b is equal to z plus 3 something. Okay, so that means this y and z are going to be used somewhere else in the program. So we assume or we update the symbol table to live, and the next uses of y and z also will be updated, and it is going to be attached with the statement I. Okay, so that is very important. This next use information is important because as we have seen in the previous in the beginning, we have seen that this basic blocks and flow graphs, this representation would be helpful in doing the register allocation and instruction selection. So if that particular variable is not going to be used anymore, then we need not assign a register for that particular value. Okay, because we have already seen that the registers are very less in number and it is very quick to access. Okay, so we have to use it efficiently. So it means that we cannot spoil the register by putting a variable which is not at all going to be used anymore. Okay, so that is why it is very helpful in the register allocation and also in the instruction selection. So whichever variable is not going to be used anymore or it is not live, then based on that we can reorder the instructions, and that would be helpful in selecting the target instructions carefully. So this is about the basic blocks and flow graphs. And the next one we have already seen about in the the total phases of compiler. One phase we have talked about code optimization. Okay, so after the intermediate code generation phase, we have seen a phase called as code optimization phase. Okay, we have seen about the code optimization. So what is this code optimization? We when we convert or translate the original program into this three address, we will have a long list of instructions. Okay, so we have a long list of three address instruction. So if we don't optimize it, then we will be keep on repeatedly doing some or repeatedly executing some instructions unnecessarily. So this is very important topic, this code optimization. So we can obtain a substantial improvement in the running time of the code. Okay, that is also important. So one thing is space and another thing is the running time. We can improve this running time of the code merely by performing some local optimization within each basic block by itself. So now already we have partitioned the three address instructions into various basic blocks. Now we can optimize each basic blocks. Okay, instead of going through the entire program, we can simply do some local optimization. So the first one is we are going to use a DAG representation. So already we have studied what is a DAG and how to draw a DAG and so on. So if this basic block could be drawn as a DAG, then we will be able to identify the, already we have seen the DAG representation. What is the use? It would be helpful to find out the common sub expressions. Okay, it will be helpful to find out the common sub expressions. So if we are able to represent the basic block as a DAG representation, then we can identify the local common expressions and eliminate it. Okay, we can eliminate the local common sub expressions, and also we can eliminate the dead code, that is the instructions that compute a value that is never used. Okay, they simply compute some value, maybe inside a basic block for some temporary values or some intermediate results might have been calculated or computed, but that is not going to be used anywhere. So such dead code can be eliminated. And then we can also reorder the statements that do not depend on one another. So this is also one of the main tasks of this code generation phase, reordering the statements so that you can even do or execute parallelly, and which will help in improving the time taken for execution. And finally, it will apply algebraic laws to reorder the operands of three address instructions, and sometimes thereby simplify even the computation. So this DAG representation would be very helpful when we try to optimize the code locally. So for example, you take this example. We have a set of four three address instructions: a equal to b plus c, b equal to a minus d, c is equal to b plus c, and again d is equal to a minus d. So now if you draw the DAG, what you are saying, a is equal to b plus c, first one we have drawn, and then the same value a is going to be used for calculating a minus d. So a minus d, this is equal to b. Okay, it is nothing but it is equal to b. And c is equal to b plus c. So the value of b, and again the value of c is used. Okay, so you should know the difference here. We are not, we here we are, we have an initial value b, and we are now changing the value b. So we are not using the same b value. That's why you are not using the same b variable. So this is the initial value, then we have an updated value present in this b. Okay, and then finally d is equal to a minus d. So so now here we are having this a minus d already is there, whose values are not changed anywhere. Okay, a's value as well as d's value is not at all changed. So this b and d are actually going to be the same value. Okay, so that is why b and d. And c is equal to b plus c. Okay, the b value is here and c value, so that is c value. So by this we are you can see the optimization happened. So a equal to b plus c, and d is equal to a minus d. So why we are not uh, so anyway, we need to have the variable d, and that can also be used here for this instruction, because b and d are going to be same. Okay, b and d are going to be same. So instead of having two separate instructions for b and d, we make it as, because this if we take uh, this d instruction, then we can also use it here instead of b. Okay, so a is equal to b plus c, d is equal to a minus d, and c is equal to d plus c. So the four instructions are now reduced to three. That is, we have optimized this code. Okay, which is present in a single basic block. So similarly here also, if you see, a is equal to b plus c. Okay, so b and c are added, and that is a, that is a, and then we have b is equal to b minus d. So b minus d, already we have the variables b, c and d. So first one we are adding b and c, and then we are adding b, subtracting b and d, so that is equal to b, and then we have c equal to c plus d. Okay, c plus d, and then finally we have E is equal to B plus C. Okay, so this is E node. So now, why we are saying this example is that we are going to see how we can eliminate the dead code. Dead code elimination. Okay, so what we are seeing is the local optimization. Okay, how we can do the optimization within a basic block. So the dead code elimination is that from the basic block DAG, okay, we have constructed a DAG for the basic block. You can remove any root node that has no live variables. So just now we have seen the live variables, and we have seen the live variables and the next use information which is present in the symbol table. Yes, Nirmal, what do you want to say something? Okay, listen. So I'll give you that example. Now you assume from this thing, okay. So now all or our assumption, we have a basic block which has some set of three address instructions, and we have constructed a DAG for this basic block. Now in this basic block, this E is the root node. Okay, this E, we have found E is equal to B plus C. Okay, E is equal to B plus C. So this is the root node. Now let us assume that here A and B are live variables, that is it is having some next use. Okay, and we let us assume, okay, this is our assumption for this particular set of variables, and let us assume C and E are not live. Okay, that is it is not going to be used anywhere else. Okay, in that case what we can do is, if the root node, it is not live, it is not a live variable, then you can just eliminate it. If you eliminate it, along with that this edges, everything will be eliminated. Now which are the root nodes? A, B, C, all three are root nodes. Now again, among this A, B and C, C is not a live variable, so we can even eliminate this node C. Okay, then that means we will be having only A and B finally. So by this we will be able to, so that is what we have seen from the basic block DAG. Remove any root node that has no live variables. Repeat until no nodes can be removed. So this we are going to do it again and again to eliminate all the dead codes which are not at all going to be useful anymore. Okay, so that is how you can optimize the code. And finally, the use of algebraic entities. So using this algebraic entities, we can optimize the code to maximum amount, and so that we'll be able to reduce the computations that are needed. So this is a general rule, right? Whatever it is added with zero, it is going to give you the same answer. So if it is multiplied with 1, again it is going to give you the same answer. Okay, x plus 0 and 0 plus x is going to be anyway x only. And if it is x equal to 1 and 1 into x, then again value is going to be x. So instead of using, but the system does not know. If it simply sees the plus operator, then it will do all the same set of instructions what it is trained to do, what it is instructed to do. So it will, what it will do, it will load this 0 into a register, then it will add the values x and this register, and then it will store that in a x. Okay, all these are unnecessary because this kind of instructions need to be eliminated, or these kind of computations need to be eliminated. Okay, and similarly, like any number that is divided by 1 would be the same value, and anything that is subtracted by 0 would be the same value. So these kind of computations needs to be eliminated, so that you will be able to optimize the code better. And then reduction in strength. What is this? What this says about is that we have something called x square. Okay, so instead of doing the exponential, so we have something which is easier than this. Okay, so multiplication is complicated, but more than that, this exponent computation would be more complicated than that. So instead of representing as x square, if it is going to be x into x, then the computation would be less, and that would be much better than doing x square. Similarly, when you compare multiplication and addition would be much better or easier or less computational power than this multiplication. So x plus x would be better than doing 2 into x. Both are going to give you the same result. And instead of doing division, we can do it with multiplication. So whichever is going to decrease your computational power and will increase the which will increase the runtime of your program, that we need to choose. So these are all some local optimizations. And constant folding, so you would be using the pi value. So we constantly know, we every time we know that pi is going to be 3.14. So instead of again and using this variable and accessing that value from some register or from memory, we can directly execute that value once, and we can keep on using that instead of uh, every time calling the pi variable. Okay, so that is a constant folding. So we can evaluate it at the compile time and use it anytime. And we have other algebraic transformations also. Okay, x into y or y into x, all are same. So instead of every time, you need not complicate the process. Okay, and there are some examples you can see that. So the two topics we have seen, these are all will be coming in the end semester exam. So after the third internal portion, so please study this. Okay, now quickly give me the attendance. Have you listened? Did you understand? Can I get some answers in the chat box? Those who have listened and those who have understood, please reply in the chat box. Nobody? Only one? Okay, thank you, students. So please quickly give me the attendance. James Jayadas,
Present,
Kiran,
ma'am.
Biswayan, Anselin,
Present, ma'am.
Present, ma'am.
Sanat, Sanat,
Present, ma'am.
Ma'am, one
Yes,
present,
ma'am.
ma'am. Mike got turned.
Chris Thomas, Ruben, Alan Bobby.
Ma'am, Ruben's mic is not
Present,
working.
ma'am. Ma'am, Alan present, ma'am.
Okay. Ruben, where is he there in the call?
Yes,
Okay.
ma'am, he's there.
Yes, ma'am, I'm here. My mic is
Okay.
having.
Rubek Daniel,
Present, ma'am.
Albi Shinoj,